Good day, guys. So for today, we'll have the first day in online class. So this is the distance education module for Gen Chem 1. So for today, we'll tackle the first day. So we have the first part in chapter 5, electron configurations and the periodic table. So in this video, we'll just limit to 5.1 electromagnetic radiation and matter. So in the next two videos that I will upload, so we'll have the Planck's quantum theory and also the Bohr model of the hydrogen atom. So if you have more time reading, then you may consider reading the chemistry, the molecular science, 4th edition by Morse and Stanitsky. So it's the same book that I showed to you during the class last time. So the pages are there, and some of the uh, problems, or most of the problems, so we will try to answer that. But first, you're going to answer it just like what we're doing in the class. So first, you'll try to solve it, and then in this video, so we'll also answer it. Okay, so I hope you guys also have the PowerPoint presentation with you, so that I uploaded in Edmodo, so that if you need to try to zoom in, or if you cannot see clearly the video, then you may consider reading your uh, PowerPoint presentations. Okay, so let's start this discussion. So again, we'll try to focus first in 5.1. Okay, so this chapter 5, we have so much topics. Then these are the objectives. So I already told you this one. Okay, so again, 5.1, electromagnetic radiation and matter. So before we understand what is radiation, so we first try to understand what is wave. So wave, from the definition in the dictionary, so this is the vibrating disturbance by which energy is transmitted. So for example, this one is a wave, so we have this curvature. So for example, this one or this point has a certain energy, then when it goes to this point at this curve, so it will be transmitted, and that disturbance, or that vibrating disturbance, is called a wave. So from this wave, so we can see clearly that the direction of wave propagation is from left to right. So we can also have some up from bottom up, or from up bottom, or we can also have different directional waves. And we also see in this figure that we have different properties of a wave. So particular, we have first the wavelength. So this wavelength is characterized by Greek letter lambda. So this is the distance between two identical points on successive waves. So for example, this one, this topmost point, and this successive wave on the topmost point also, if we measure the length of this 2 points, the distance between them, then that is the wavelength. So the unit for this is nanometers. Okay, so nanometers, since the waves are very, very small. But we also have waves in meter scale. Okay, so we'll see that later on. Okay, but we will focus more on waves which are very small, and the wavelengths are in mostly nanometer scale. So we can also have meters. Aside from meters, we can also have angstrom or picometers as units for wavelength. So I hope you try to recall those prefixes that we tackled in chapter 1. Okay, so the second property of a wave is frequency, characterized by this Greek letter nu. Nu and u. So this frequency is the number of waves that pass through a particular point. For example, we have this point here. Okay, so we count 1 second and we count all the waves that pass through that particular point. So, for example, uh, there are 30 waves that pass through that point. Then we have 5 cycles per second, or we call it as 5 per second or 5 hertz. So this is the unit for frequency. Or we can also have a single wave, and then for example, we count 1 second and and we count all the number of waves that it appeared to, and that is also called the frequency. So we count the number of cycles per 1 second. So this hertz can be also per second. So the last is we have the amplitude. So amplitude, or capital letter A, is the vertical distance from the midline of the wave to the peak, or the midline of the wave to the trough. So the unit for that is, since it is a measure of length, so it is in nanometers also, since it is also very small compared with the wavelengths. Okay, so this amplitude, so if we square this, so this is directly proportional with the intensity of the wave. So for example, we have light wave, so the intensity of the light is directly proportional with the square of its amplitude. Or we can also have the waves in the earthquake, or the waves in the ocean. So those are waves, those are disturbances that uh, occurs when energy is transmitted. Okay, so we'll try not to talk about this amplitude, since this topic is covered mostly in physics, where we try to uh, determine the intensities of the waves. So we'll just focus on the lambda and the frequency. The lambda, or the wavelength, and the nu, or frequency. So if we multiply this, so the product will be u, or the speed. Okay, so the speed of the wave. For example, this wavelength is in nanometers. This nu is hertz, or per second. So the speed is sometimes, the unit for speed is sometimes nanometers per second. We can also convert that into meters per second, or kilometers per hour, or it depends. Okay, so let's try to have some uh, theories behind electromagnetic radiation and matter. So James Clerk Maxwell proposed that visible light consists of electromagnetic waves. So this electromagnetic wave, so it is a wave, or a disturbance containing both electric field and magnetic field. Hence we have the electromagnetic wave. So electric meaning there are charges, magnetic, so there are poles, positive and negative, and okay, of the magnetic field component. So meaning it could transfer energy. So if you're familiar with Maxwell from physics, so he proposed 4 theories, or four formulas for the physics in electromagnetism. Okay. So electromagnetic radiation, or we sometimes call this as EMR. So this is the emission and transmission of energy in the form of electromagnetic waves. So note that these waves travel to 3 times 10 to the 8 meters per second in a vacuum. So this is called the speed of light, denoted by symbol C. So this C, or this speed of light, is a constant. So you must remember this constant. So this has an infinite number of significant figures. So if we are going to make some problems dealing with this. Okay. So much for the problem. Okay, we first look at the different types of electromagnetic radiation. So wavelength. Okay, so if we try to convert wavelength to frequency, then we use the formula from the last time, yung U is equal to lambda nu. Okay, so if we have the wavelength 10 to the negative 3, so these are gamma rays. Okay, and then 10 to the negative 1 nanometers are X-rays. Okay, so we are particular with the X-rays as well as ultraviolet rays. So we use X-rays in the detection of fractures in bones, for example. For ultraviolet rays, so that is from the sun. So we know that ultraviolet rays can alter our DNA as well as these X-rays and gamma rays. And then we have here visible region, and then we have the infrared, and then microwave. We also have TV waves, and the 10 to the 11 nanometers, or the wavelengths with meter scale, the radio waves. Okay, so let's try to see the visible light spectrum. Okay, so this is the only spectrum that we can see as human beings, since the others are invisible to our naked eyes. Okay, so here, so beyond this 400 nanometers, so we have the ultraviolet, and then this is color violet, going to blue, green, yellow, orange, and then red. And then going beyond the 700 nanometers are the infrared light. Okay, so we need to know this 400 nanometers to 700 nanometers range, since maybe in a quiz or in an exam, so we try to convert this 400 nanometers into frequency. Okay, so let's try to have some problems with that. Green light has a wavelength of 495 nanometers. Calculate the frequency of this light. Okay, so in this problem, we're given the wavelength and indirectly given the speed of light. Okay, so from the previous formula, so calculate the frequency of the light with wavelength 495 nanometers. Okay, so you may pause this video and then try to get back, and then we'll answer it. So you may do answering this problem first. Okay, so I hope you have done the calculations first before proceeding with this video. Okay, so this is the solution. So first, we have the u is equal to lambda nu, but this speed, okay, so we know that is the speed of light, so c is equal to lambda nu. Okay, and then we try to discover this nu, so this means that we need to divide both sides by lambda, or by the wavelength. So nu now, or the frequency, is equal to c over the wavelength, and then we just plug in the values. So c is 3 times 10 to the 8 meters per second. Our lambda, or the wavelength, is 495 nanometers. So meters and then nanometers, we cannot exactly cancel that. So first, we need to convert nanometers into meters by using this conversion factor. 1 meter is to 1 times 10 to the 9 nanometers. So plugging in the calculator, so we get 6.06 times 10 to the 14 per second, or hertz. Okay, so next is, we also have a problem, but this time this is reverse. In the upper atmosphere, there is solar radiation with a frequency of 9.99 times 10 to the 14 hertz. Calculate its wavelength in meters and in nanometers. So you may want to pause this first and then we'll also solve this problem. Okay, so I also hope that you pause this video and determine first the answer before proceeding with this video. Okay, so this is the formula. So C is equal to lambda nu. Okay, but this time we need to find the wavelength. So we divide both sides by the frequency. So C is over nu or frequency. So we try to plug in the values. So 3 times 10 to the 8 meters per second over 9.99 times 10 to the 14 hertz or per second. Okay, so we'll just cancel the per second. So we will have 3.00 times 10 to the negative 7 meters. So that's our answer in problem A. So for B, since we already know the wavelength in meters, we just convert this into nanometers by using again this conversion factor. 1 meter is to 1 times 10 to the 9 nanometers. So cancel the meters, so we'll get 300 nanometers. Okay, so I hope that you know this electromagnetic radiation problems. So this is just a conversion by using the single formula C is equal to lambda nu. Okay.